Okay, take it away.
Okay, thank you. Yeah, my third time. Wow. Um, you talked about Bill Keane. So I just retired 2 months ago. So this is the first like workish thing I've done since I retired. So woohoo for that. Um, when I came for my job interview 36 years ago at UWM. At that time, atmospheric science was in the geosciences department, and Bill Keane was the chair of the department. So he's the one who picked me up at the airport and took me out for meals. I remember that at dinner at some restaurant, um, Bill ordered a Bloody Mary and it came with a beer chaser and it came with all this food inside the glass. And that was a Milwaukee thing that I had never heard about before. So fond memories of Bill Keane. Anyways, can you guys hear me okay? It sounds kind of quiet.
Yep, hear you.
Okay, good. Um, all right. So I heard that you guys, or some of you, are birders. So that's good. That means that you look up sometimes towards the sky. And that's good because that's the first thing that you need to do in order to view all kinds of cool stuff that you can see in the atmosphere. So today I'm going to talk about mirages, and uh, this picture on the screen here, well, it's a drawing from a book. Um, I stole this image from a book by Robert Greenler, who is a retired physics professor at UWM and the originator of the uh, science bag program. And Robert Greenler did a really nice mirage archaeology or forensic analysis of this drawing. This is a famous drawing in the Mirage literature. And what he determined was that there's no way an image like this could occur at one time. And what he concluded was that the person who drew the image over some amount of time, like an hour or two, because it takes a while to make a sketch as detailed as this. And during that hour or two, the image changed. You can see the real images, the boat underneath at the bottom, and then above it are the false images. One of them is inverted, one of them is not. And interestingly enough, those occurred at different times, which is not evident from the image. So anyways, a little bit of nerding out over mirages there. So, oops, let's see. How do I?
Oh,
Uh, there we go. Okay, before we start, I'm going to dazzle you guys with some assorted photos of cool stuff that you can see in the sky. Uh, Things that are not mirages. Can you guys see my mouse wiggling around here? Yeah, can you see it?
Roger. Yes.
Okay, great. All right, so here are these things that are sunbeams. Those are called crepuscular rays, commonly known as sunbeams. Those are in the air all the time when the sun is out. It's just that you need something, some particulate material in the atmosphere in order to see them. Sometimes it's just naturally occurring dust in the air. Other times it's pollutants or these days we get a lot of smoke from forest fires, but when you have pollutants, then you can see these. And interestingly enough, all of these rays, these sunbeams, are parallel to each other. And it only looks, it's an optical illusion that they look like they're not parallel. Sorry about that. Um, they all emanate from the sun and they travel in parallel lines. When these crepuscular rays occur, hold on a second, I gotta silence this. Sorry about that. When the sun is below the horizon, the same phenomenon occurs. But here the rays or the sunbeams, they emanate upward, and these are called anti-crepuscular rays. But again, all of these rays are parallel. Okay, this is something that we see around here sometimes. It's called a sun pillar. This is what happens when you have ice crystals floating around. And the ice crystals tend to be shaped like little microscopic hexagons. And when these little hexagonal ice crystals fall in the atmosphere, they fall very slowly. So it's as if they're floating, as if they're not falling, but they are falling slowly. They fall in two modes. One mode is tumbling, and the other mode is floating. And when they float, the sun, the setting sun or rising sun, if it's on the other side of the sky, reflects off of the bottoms of these ice crystals to create this shaft of light called a sun pillar. When the hexagonal, the little mini hexagon ice crystals tumble as they fall, you get this halo, which is also common around here. So let's see, what else do we have here? This is a nice one. This is called earth shadow. This is something that you can see. Well, these are mountains here, so this isn't from Milwaukee, but when you see a sunset, you can see what's pictured here by turning around. Because when the sun is setting, the shadow of the earth rises into the sky. And so this is the rising earth shadow here. Okay, well, let's get to the main event. Okay, mirages. So let's see. It's weird that it's so quiet. So you guys can still hear me, right? I just got to check every now and then.
Yeah, it's all good.
Okay, make sure that nothing bad happened. Okay, so a mirage is something that you see in the sky that isn't actually there. So it's a false image. And there are two kinds of mirages. Well, two main kinds, inferior and superior. So an inferior mirage is one where the false image occurs below. So inferior means below in this sense, occurs below the actual image. And a superior mirage is one in which the false image appears above the actual mirage. So here in this picture, you see some islands here. Here's one. And on the right side, there's one and another one. And those are the actual images. The false images are above, so superior mirage. In this case, you can see that the false images above are inverted as well. Here, this is the more common kind of mirage, at least for our part of the world. It's inferior mirage because here is the actual image. It's whatever this thing that the space shuttle here is towing or is sitting next to. And here's the false image beneath it. Here's the sky, and it's a false sky below it. So below inferior. Okay. So let's get into some details. First, here's a little quiz for you. What do you think? Does light travel in a straight line or does it not? Can you chime in, someone or someone's?
Yes, except when it doesn't.
It covers all the bases.
Would it matter if it's going through an atmosphere that would curve it?
Well, light that you see in the sky is always going through an atmosphere. The question is, does it curve or not?
It does if
Um,
there's extreme gravity.
Yeah, I think so
Curves.
too. Magnetic field.
Extreme gravity, magnetic field. Okay, well, so those are interesting thoughts. So the answer is yes. light does travel in a straight line, but only if it's in what we call a homogeneous medium. So let me deconstruct that. So a medium is the stuff that the light is passing through. So like if you're underwater, the medium is water. But if you're looking at the sky, the medium is air. And homogeneous means density, if the density is the same. So for example, in this diagram here of the pencil, it looks like the pencil is bent because in part of the image, you're looking at the pencil that is in air, and in part of the image, you know, the lower half of the pencil is in the water, you're looking at it through water. So the light that is traveling from the pencil to your eyes is traveling through air, and also for the lower part, it's traveling through water, and water is 1,000 times more dense than air. So the medium, which in this example is both air and water, is definitely not homogeneous because part of it is 1,000 times less dense than the other part. Okay, so when light, so the reason that you see this pencil as being bent, it's a mirage, it's not bent. But the reason it looks bent is because the light rays that are coming from the pencil to your eyes are curving or bending. And the correct word to use for that is refraction. So the light is refracting because the density is not the same. Okay. All right. So that's the key to understanding mirages, is that light rays bend or refract when they pass through air where the density is changing.
That's what makes eyeglasses work.
Yes, sure, right. So let's talk a little bit about the density in the atmosphere. So here's a graph, this top one, that shows the pressure at different altitudes. So at ground level, the pressure is the highest. This we're talking about atmospheric pressure, not density here. And as you go up, the pressure is less and less. And eventually, if you get up so far that you're out of the atmosphere and you're into space, there's no pressure at all because there's no atmosphere. Okay, so if you remember your chemistry, density, which is what we're concerned about here, is related to both pressure and temperature. So the pressure relationship here is as you go up, the pressure decreases, and when you decrease the pressure, you lower the density. Okay, all right. Now, the one on the bottom is a similar graph, but this shows temperature. So at ground level, the temperature is typically warmest. And as you go up, usually the temperature decreases. Now, of course, this changes with the weather, but what I'm showing you here is the average conditions. So when you consider the relationship or the extent to which temperature controls density, as you go up, the temperature decreases, and that should increase the density. So you have an interesting situation here where the pressure would cause the density to get lower as you go up, but the temperature would cause the density to increase as you go up. So it turns out that there is a sweet spot if the temperature decreases at a certain rate. So in meteorology, we call this a lapse rate. That is the rate at which temperature lapses or decreases as you go up. And that sweet spot is about 2 degrees Fahrenheit per 100 feet. I had to do that conversion because meteorologists, we don't think in Fahrenheit and feet, but anyways, there you have it. So if the temperature decreased as you go up at that rate, about 2 degrees of temperature cooling per 100 feet of increasing altitude, if that were the case, then light would travel in straight lines. However, It doesn't. The average rate at which temperature decreases is about 0.5 degree Fahrenheit for every 100 feet that you go up. So we can conclude, therefore, that light almost never travels in straight lines because the lapse rate doesn't support it. If it were 2 degrees per 100 feet, it would, but it's not. Okay, so it's a long-winded answer. The answer is no. In our atmosphere, the light does not travel in straight lines. Okay, so let's talk about inferior mirages first. Inferior mirage is the one where the false image is below the actual image. So those are the most common types of mirages around here in our part of the world. The most common kind of inferior mirage is something that's called the desert mirage. You know, where you've seen the cartoons, you know, where the raggedy looking guy is crawling through the desert and he thinks he sees water up ahead, but there's no water. That's the desert mirage. So here, what you have, this graph, is a typical temperature profile. So this is a graph of temperature as you go up for a desert mirage. So what you have is really hot temperatures at the ground. And so 80 degrees Celsius. So that's like, you know, 150 or so degrees Fahrenheit. Now, you might say that that's too hot, but you know, I'm sure that you've had a situation where you're outside at the beach and you're barefoot and the sand is so hot that it hurts the bottom of your feet. And if you venture out to you know, a black asphalt parking lot, it would definitely hurt your feet. So these temperatures actually occur on hot, sunny days. Okay, so here the temperature is, you know, more than 800 times what you would need for light to travel in straight lines. So obviously light doesn't travel in straight lines, this kind of situation. Now, for the superior mirage, there you need what's called a temperature inversion. So a temperature inversion is when the normal shape, the normal state of affairs, where as you go up, the temperature drops, where that state of affairs is inverted. And as you go up, the temperature increases. Now, that's actually a common phenomenon around here. For example, it happens at night. Not all nights, but sometimes when you don't have clouds and when it's not windy, you can get a temperature inversion. But if you have a strong one where the temperature increases a lot as you go up in altitude, then the conditions are right for the superior mirage, where the false image appears above. Okay, so this is a diagram that shows how inferior mirages work. So up in the right, you have this sketch of a graph where it's temperature as you go up in altitude. So temperature decreases as you go up. And notice, according to the graph, that as you go up just a little bit, the temperature decreases a lot. That's a typical temperature profile on a hot summer day, especially if the ground is dark, like a black or gray road surface. Okay, so here is the observer, and suppose the observer is looking at something like this tree. So the reason that the observer can see the tree at all is because there's a light source, which is the sun. So what happens is the sun shines on the tree, and the tree reflects the light, and the light goes in all directions. And one of those directions is back towards the observer's eye. So the observer looks in the direction of the tree and he sees the tree. Okay, but some of the light refracts or bends for the reason that I've been telling you, because we have an inhomogeneous medium because of this temperature profile. So Some of the light travels right towards the observer's eye, but some of the light bends and it goes down here. Okay, and then it bends some more and it comes back up. So the observer, when he looks in the direction where this bendy ray is coming, it looks that like the tree is underground, inverted. Okay, so you see the observer sees the real image, but when you look a little bit down, you see the false image, inverted, because of the refraction or bending of light. So this is a common phenomenon. Now I have a bunch of photos to show you. By the way, if you have questions or something, you're welcome to chime in. It doesn't bother me a bit. It just gives me a chance to take a sip of coffee or something. Okay, so here you have sort of a classic desert mirage, where here you have actual images of these rocks and also just the gray background. And then here you have the false image below. So this is exactly what's happening. So you have an observer, just like the diagram, you have an observer that's looking in this direction, and he is seeing the light reflected off of this image. But if you look down, he is seeing the light that has come off of this image and bent downward and then back upward towards your eyes. Some more inferior mirages that are interesting. So here you have a couple of inferior mirages over water. So what's going on here? Well, to get an inferior mirage, the ground has to be very warm compared to the air just above the ground. So you can deduce from here that this must be the winter, because the warmest water can get is 0 degrees Celsius. I'm sorry, the coldest, the coldest water can get is 0 degrees Celsius. If it gets any colder, it will freeze, right? So if you have an inferior mirage and it's over water, it means that the surface, the water, must be a lot colder than here. Did I say that right? A lot warmer, sorry, that's right, a lot warmer. So it's winter, the air is cold, but the water is warm by comparison. Actual image, false image. Same here, you see the lighthouse, see the false lighthouse below. Here's another picture. I like this because I took this one myself, because you have the inferior mirage, the so-called desert mirage. Here, a couple, here's one, here's one, here's one, and you have a dust devil off at the corner. I took this on a road trip through West Texas one time. These people are pulled off taking a photo of the dust devil, and I'm pulled off taking a photo of the mirages. Actually, I don't know. I think I might have, can't remember if I took that one or not. Another inferior mirage, wintertime. Okay, here is what I consider to be a really interesting fact about inferior mirages. Inferior mirages look like water. And that's why they're called the desert mirage, because of the, the caricature of the raggedy desert guy crawling around trying to reach the water, only to find that it's not water. And Robert Greenler, the guy that I mentioned before, who wrote a book, actually a couple of books about optical phenomenon in the atmosphere, he had what I thought to be an excellent interpretation of why it looks like water. So, as Greenler says, the only other place in nature where you can see something reflected above its inverted image is over the water. So your brain takes what you see and it makes the interpretation that it's water. And your brain is, of course, wrong in this case, but that's Greenler's explanation, and I'm going with that. I kind of like it. Here's another one. Pretty sure I took this photo. Also West Texas. Notice that the inferior mirage here is a false image of the sky. And we know that. I think everyone would agree with that. But nevertheless, it still looks like water. Okay, so how are we doing? Everyone still there?
Sort of. Trying to follow.
Yeah,
Okay.
we are.
Okay. All right. So with inferior mirages, there's a really cool phenomenon that's called the vanishing line. And unfortunately, there aren't great photos available of this, at least not that I've found, but I'll do the best I can here. So we're still talking about inferior mirages here. So here's the observer. The observer is looking at an image, and you can see from these lines, which show the path of light rays from the image, the tree, to the observer's eyes, that when the observer looks up, sees the actual image, the tree. When the observer looks down, sees the inverted image of the tree, following this ray here. Okay, but when the observer looks straight, he doesn't see the tree at all. The tree can only be seen when he looks up or when he looks down. So there's this really interesting phenomenon where if the observer was looking at this tree, if the observer were to slowly crouch down, like maybe 6 inches, and then look at the tree, and then crouch 6 inches more and look at the tree, and so on, there would come a point where the tree would appear to disappear. And that's called the vanishing line. So here's a picture. This is from Greenler's book, showing some islands in Lake Erie. So you see islands, you see an inferior mirage below it. It's like, it looks like the sky, right? And then here is the same photo taken by Greenler where he's crouching down a little bit. And the islands appear like they're gone. Okay, I have another photo. So this is from some bridge in Japan, where here you have the person who took the photo climbed on a ladder or something, and he's taking a picture at 3 meters. So here's the actual bridge. Here's the false image, the inferior mirage below it. And then each successive diagram, he's taking the photo from a less and less height, where finally he's only at 20 centimeters above the ground, and the bridge appears to disappear. Vanishing line, very cool. I have tried to reproduce that myself a number of times, and I haven't done it yet, but it's a goal of mine. I recently retired. I have plenty of time.
Yeah, go to that bridge. Go to that one.
Sounds good. Okay, here is a photo that I found of the Mackinac Bridge in Michigan, where you have something similar, where this is the actual image. You can see the whole bridge, but here you can see an inferior mirage below it. So here's an inverted part of that pillar on the bridge. But you can't see the entire bridge. So this is a not that great example of the vanishing line, but I think it makes the point. Okay. Ready to move on to superior mirages? Well, we're going there whether you're ready or not, I guess. Okay, superior mirages. Now, superior mirages are special. I'll say special for two reasons. One is that they're not very common around here. The parts of the world where superior mirages are common are areas where the ground is usually colder than the air above it. So like the Arctic, the Antarctic, those areas. Around here, they're kind of rare. So that's one reason why they're special, because they're rare. The other reason is that unlike inferior mirages, there are a whole bunch of different kind of superior mirages, as I'll demonstrate. So here you have a graph showing temperature as you go up in the atmosphere, and the temperature increases as you go up. But in this example, this graph, it does so in a irregular way. First, it stays more or less the same as you go up, then it increases a lot, and so on. So it's an irregular shaped graph. And with this particular temperature profile, you get this kind of superior mirage, where here's the actual image, here's the false image. The false image is superior above the actual image, and in this particular case, it's not inverted. Okay. So when you have something like this, where the superior mirage is not inverted, it's called looming. All right, that's just a jargon. So here's some looming images. So this one is interesting because here you see an iceberg, and the iceberg is a mirage. The actual image is actually below the horizon. The curvature of the earth prevents you from seeing it, but you can see the false mirage image. It's not a false one of this guy here. Here's another example of superior mirage. You have the actual image and you have the false image here. Here you have something that's called, well, it's a superior mirage, but they call this floating islands, where you have this island that appears to float. It only appears to float because it's a false image. Okay, let's see. Now, towering images are a type of superior mirage where it's not an entirely false image. It's just that the shape of the actual image is modified by the bending of light rays, the refraction of light rays. So this is similar to a funhouse mirror. Okay, you know what I'm talking about, where you go to like a county fair or something, and there are these goofy curved mirrors where you can look and you can see your body all stretched, right? So the atmosphere does that for you all by itself. And it stretches the images. That's called towering. So here's an example of one where you have a setting sun. I suppose it could be a rising sun, I'm not sure, where it has an irregular shape. So this is a form of a superior mirage. Now, you can also get inverted images. So inverted image, for the image to be inverted, you have to have a temperature profile, temperature as a function of altitude in the air, that has a particular shape, where the temperature is coldest at the ground and it steadily increases as you go up. None of this curvy, funny business like we saw before. And when that happens, the superior mirage is inverted. So here you have one You have the actual boat here, and then you have the inverted boat above, some islands that are inverted above here. Okay, so this is probably, I'm just being a meteorologist here. These are probably summertime images because in the summer, you know, the ocean in a cold area like Finland probably doesn't get very much warmer than 0 degrees Celsius. So the coldest part of the atmosphere is at the ground. As you go up, the temperature commonly increases. And so I'm guessing these are summer images. Here's another one. Superior Mirage. I've seen superior mirages in Milwaukee probably half a dozen times. And every time I've seen it, it's been like if I was walking or driving along Lincoln Memorial Drive, looking out over the water. And if it's the springtime, then the water is typically very cold still, and the air above it is much warmer. And those are the conditions that you need for a superior mirage, but I have not seen them very often around here. So this is the image that was on the first slide that I talked about. So this is interesting because you have the actual image, and then above it, you have an inverted false image and a not inverted false image. And again, this has to do with a combination of the complexity of the temperature profile and the fact that this diagram was probably made over a period of a couple of hours where the view changed. Okay, so have any of you guys heard about the Fata Morgana? This is the granddaddy of all mirages. Or the Holy Grail. For meteorologists, we have 2 holy grails. One is a tornado. Actually, I should say 3. One is a tornado, one is a green flash, and the other is a Fata Morgana. And I'm proud to say that I'm 2 for 3. I've seen a tornado and I've seen the green flash. I've never seen the Fata Morgana yet. So Fata Morgana is a character from an old Shakespeare thing. Shakespeare literature associated with castles and crystal palaces and so on. So Fata Morgana is a type of superior mirage which is spectacular. For example, in this one here, the whole horizon looks like this, just jumbled snow. There are no mountains or anything. And in this image, there's nothing like this at all. This is completely false. Let's get some more examples here. So here's an image from Antarctica. As I told you before, the polar regions are great places to see superior mirages. So here, this was the photo was taken on a field of ice flats. So just huge expanses of flat, featureless ice. And you see this thing that looks like an ice mountain, just a mirage. Now I'm going to hope this works. I have a video. Oh, it's working. Are you seeing this?
Yep.
Okay. So here's a video of the Fata Morgana on Lake Superior. You see a couple of false images above the actual ship. One's inverted, one above it is not. You have some stretching here, right? The towering image there. Let's back it up a little bit. So I don't know if you guys have seen anything like this. I have not. Very cool. Okay, so let's get back to this. All right, so now I'm going to close out this talk with a couple of sort of oddball kind of mirages. So here's a combination of a mirage with a solar eclipse, partial solar eclipse. So you see the sun with a bite taken out of it here as the moon passes in the field of vision, and you see this other thing below it, which is an inferior mirage, right? False image below. Okay, now you guys know about the green flash? Anyone? So the green flash is an optical phenomenon. Most people that like students at UWM that I've encountered that know about it, they air quote know about it from the Pirates of the Caribbean movies, where the green flash appears with the sound effect of ah. So the sound effect doesn't actually happen. But what happens here is that when the sun sets, so here you have successive pictures of the setting sun. At the very last moment, when only the top little piece of the setting sun is available, then you get a little flash of green light. And it's not brighter than the other light. It's just all by itself and it's green. And it's very elusive. So here you see an inferior mirage associated with the setting sun. Notice here you have these little extensions here, which are false, and then you have the green flash. Here's a green flash. Also, the other little bit of the setting sun, look at the shape. The actual shape of the setting sun is not like this. It's distorted due to the refraction. Here's a green flash all by itself. Okay. All right. So now I have something for you that which is not exactly an inferior mirage or a superior mirage. It's kind of both. It's called ducting. So imagine if you are here and you are looking to the left. You're looking in this direction. Observers here. So this graph shows what the temperature profile would be. So here you have the temperature decreasing as you go up. So that would imply that any mirage that you would see would be an inferior mirage. But then here you have an inflection point where the temperature starts to increase again as you go up. So here, that would imply that any mirage that you see would be a superior mirage. So if you're standing over here on the right side and you're looking over here, then the light coming from some object that you're looking at might bend first in one way and then in another way because your line of sight is very close to this inflection point in temperature. And when that happens, you get these distorted shapes, and that's called ducting. So here's a setting sun where you have this phenomenon combination of inferior and superior mirages. So here's one where you have that ducting going on. You see the irregularities in shape, but you also can see an inferior mirage, which is also irregular in shape below it. This one I took. You have just a little bit of ducting here where you have like little extensions of the bottom of the sun, looks like it, going off to the right, going off to the left. The actual sun doesn't do that. So it's Mirage. And I think that might be, yep, that's my last one. Okay. Well, I will stop here. That's all I have, and I'll be happy to answer any questions.